Welcome to Spark STEM Scholars.
Hey guys, today we'll be going over exponential versus linear growth. Let's get started. So what is an exponential growth? It is when a quantity grows periodically by a factor greater than 1. Our equation is y equal to a times b to the t, where y is our final quantity, a is our initial quantity, b is our growth factor, greater than 1, and t is our time. Let's take a look at an example. Let's say that the population of ants doubles every month. Our initial population is 100 ants. So our model equation would be y equal to our initial population times, since it doubles, that's 2 times, to the t, where t is equal to number of months. Let's take a look at another example of, let's say, a bank account earns 5% every year. Let's say our initial amount, we have $200. So our model equation would be y equal to our initial dollar amount times, since it earns 5% every year, that means on top of our 200, there will be 5% of 200. So that would be 100% plus 5%. And every year we'll end up with 105% of our money. So that is equal to 1.05 in decimals. So 1.05 to t, where t is equal to the number of years. So let's take a look on how our graph will look like. Exponential growth. We would have the x-axis and the y-axis. Exponential growth will look something like this, where it will slowly increase at first, but speed up over time. You see how it's pretty low slope over here and then a big increase there. So let's look at exponential decay. Exponential decay is similar in logic, but instead of increasing, it is decreasing, like so. And it is the opposite, so it will decrease really fast at first, but it slows down over time. So it is worth memorizing these two graphs since the SAT will test you explicitly on them. Now, the only difference between exponential decay and exponential growth is the graph and that the growth value, the B, the growth value is less than 1. Growth factor is less than 1. Let's take a look at a little example. Let's say we have a 400-gram radioactive substance, and Y is the mass of the substance. And let's say that it loses 40% of the mass every year. So our unit T equals to number of years. Since it loses 40%, let's take a look at our model equation. Y equal to our initial mass is 400 times, since it loses 40%, our 100% of mass, it loses 40%. So at the end of every year, we will have 60% of the mass left. So that's 0.6 to the T. So this would be our equation. So far, the examples we've discussed have been pretty easy. But what if we have more complicated cases like a bank account growing by 3% every 2 years, or a radio substance losing half its mass every 9 months? Then we will need a slightly more advanced equation, which would be Y equals to A times B to the T over K, where K is the time required for Y to increase by the factor by a factor of B. T and K, they have the same unit. So let's take a look at this example. The equation above models the mass m in nanograms, so that's our unit, of a particle over t years. So which of the following equation of mass of a particle over time? So let's take a look at our B first. Our B is greater than 1. So this is a exponential growth. And let's remember our general equation of T over K. So T over K equals to T over 3, then K is equal to 3 years. So it increased every 3 years. And our growth factor is 1.05. B of 1.05 then we would have 1.05 minus 1, which is our original mass, and it would be 0.05. And how many percent is 0.05? 0.05 is 5 over 100, which is 5%. So let's take a look at our choices. Every choice mentions increase. That's good. And increase by how much? 5% and 5 nanograms. We can take out C and D. And by how many times? 6 months and 3 years. We figured out it was 3 years. So our answer is B. Take a look at this example. Pause the video and see if you can do it on your own. Okay, let's go over this together. So the equation above is pretty similar to our last example, except our growth factor is less than 1. Our B is less than 1. And let's figure out what our K value is. So we have T over K equals to 3T. And let's multiply both sides by 1 over T so we can cancel out the T. And we have 1 over K equals to 3, which K is equal to 1 over 3 years. Now, a third of a year, we have 12 months in a year, and a third of that is 4 months. So our time factor is 4 months. Our B value is less than 1, then this is a decay equation. So that's all decrease. And 0.6, since this indicates on the mass left over. So how do we figure out the amount that's lost? So 1 minus 0.6, this is equal to 0.4. And 0.4 is 40%. So it lost 40%. And looking at our answer choices, we can get rid of A and B since it says 60, which is incorrect. It's 4 months, so our answer is C. Let's talk about linear. Increasing linear and decreasing linear. Let's take a look at the graph. It is the upslope. So remember the equation y equals to mx plus b, where m is the slope, which is quantity we're adding, and it's should be constant. And b is our y-intercept, and it is also our starting quantity. And let's take a look at an example of increasing linear. Let's say that Anne have a piggy bank, and she have 100 coins in there, but she adds 5 coins every month. So our equation would be A, which is our Y, and our M would be 5 coins a month, X, is equals to number of months plus our initial value. Let's take a look at our decreasing linear. So instead of going up, the slope is going down for decreasing. And which also means that instead of adding coins, Anne would be taking out coins, 5 coins. And so our equation for this will be negative 5x. Actually, instead of x, let's use t for time. Let's use t for time plus our initial value, or you can make this look a little nicer, 100 minus 5t. So far, not bad. Let's discuss some similarities between exponential decay and linear decay. So let's say we have a scatter plot. And this shows that as x increase over time, y decrease. This is called a negative association. And both exponential and linear decay belongs in this category. And to add on just a little bit more fact, since these dots are relatively close to each other, then you can say that this is a strong negative association. If the dots are more scattered throughout with no apparent pattern or very little pattern, then that would be a weak association. Now, vice versa, if our x increase and our y also increase, this is a positive association. And exponential and linear growth belongs in this category. And by the looks of it, the scatter plot over here is also strong. Since we talked about both linear and exponential, let's take a look at some problems. Pause the video here and see if you can do this on your own. Okay, let's take a look at this problem together. The value of a house decreased by 8% from the previous year for n consecutive years. Which of the following graphs could model this? So let's talk about a tip I have. If they give you a percentage, if they give you a percentage, then they're talking about exponential because it takes the percent of the previous value and adds on it. So every time you add something, it's a different value. So this is the exponential. Since we know that we're looking at exponential, remember the graph for exponential. A is definitely not it. B, that is not exponential. And since it's decreased, we're talking about decay. And our only answer is C. D, that's a linear decay. So we ignore that. Let's take a look at our last problem and try this on your own first. So Jimmy owes Tina some money and decides to pay her back in the following ways. Tina will receive $3 on the first day, 6 on the second, $18 on the third, and $45 on the fourth. So which of the following best describe the relationship between the time and the total amount of money Tina got from Jenny? So as you can see, every day is a different value. It is not a constant value. So it cannot be a linear. It cannot be linear. So it has to be exponential, but it's a growth or decay. Well, Tina is getting the money, so all this money is added to Tina. So it has to be increasing. So this is exponential growth.
Great job today. Keep practicing and you will be ready in no time. If you found this helpful, like, subscribe, and share with a friend who needs math help. See you next time.